In this video, we'll talk a little bit about non-homogeneous problems in terms of linear systems of ODEs. So the idea of a non-homogeneous problem in a linear system works the same way in a very similar way to non-homogeneous higher order equations like second order equations. The idea is that our homogeneous problem looks like vector x prime equals a matrix A potentially of t times vector x, and our non-homogeneous problem adds a plus f of t onto the end. If you think about this the same way we did for first or second order equations, where the part with all the x's could be put on one side all by itself. Like in this case, I could write this as x prime minus a of t x equaling 0 for homogeneous, or f of t for non-homogeneous. And the way we solve these is very similar as well. The idea is going to be to solve the homogeneous problem and then find one solution to the non-homogeneous problem. We'll talk about some of the ideas later, including the fact that we have undetermined coefficients again, as well as variation of parameters, but I want to vaguely bring up that second one in the context of the fundamental matrix discussed previously. So let's say for a given problem, we can solve the homogeneous problem in the sense of a fundamental matrix. So assume that this matrix x of t is a fundamental matrix for the system x prime is a of t times x. Our fundamental matrices will only happen for homogeneous equations. And now we want to solve a non-homogeneous problem related to this. So we want to solve x prime equals a of t x plus f of t. Since our general solution to the homogeneous problem is x of t times c, where this gives me c1x1 plus c2x2 plus c3x2 all the way down, if I want to use variation of parameters, I want to convert this into a u, which is going to be an unknown vector function that we're going to try to solve for. And the idea of solving becomes the same as it was previously. Plug this in and see what happens. I won't go through all of the full details here, but I do want to illustrate why this matrix makes things really nice. So we can plug this entire thing here into our equation. And if we do that, we will get something like the following. We'll get x of t times u prime equals a of t times x of t times u plus f of t. And this derivative here works like the product rule. So we would get something like x prime of t u plus x of t u prime of t equals a of t x of t u plus f. But because capital X is the fundamental matrix for the original system, we know that this x prime here is just a of t times x of t. As a side note, if you want to work this on your own, this is because each column solves the equation, so the full matrix does. Just based on how differentiation works component by component, and multiplication works column by column. So then this term and this term actually cancel out, because they're the same. And I can solve for u prime pretty straightforward here by inverting the matrix capital X. I'll end up with x of t times u prime equals f, or u prime equals x of t inverse times f of t. And we'll get to this in more detail when we do variation of parameters later on. But the idea that I want to get across now is that this matrix is going to be very important going forward. This fundamental matrix sort of gives us a way to solve a bunch of types of problems that we want to handle once we realize we can find a solution and stack it into a matrix. And once we can stack things into a matrix, our linear algebra skills take over and let us do a lot more with them than we could otherwise do in order to solve non-homogeneous problems, solve for the coefficients when we do initial value problems. All that stuff works out a lot nicer once we have the linear algebra backing to do this directly. We'll see when we get to this topic later on, but this inverse here, as well as the way we'd go about solving undetermined coefficients, are identical to what we would do for a higher order equation. But now we have matrices to make our lives look a little easier and things work a little simpler when we're trying to find coefficients or solve for these functions for these non-homogeneous problems.